Okay. Okay. Thank you for your patience. We are trying to solve a technical problem, which is that I need to do some exercises from this computer, and it's not just matter of sending files to another computer because we have a system here that cannot be transferred and things like that. No? So hopefully we will be able to solve this after lunch, and then we can see the implementation of some of these models, which is quite interesting, and I think looking at the numbers makes everything to be easier to understand. So in the meantime, let's keep looking at the theoretical aspects, and the last thing that we saw was these three types of approach: the notional, then the risk measures based on distributions, on loss distributions, and the third one, the scenario-based, okay? And somebody asked me a very interesting question during the coffee break about, how reliable are the scenarios, or how can the scenarios, the probabilities, how can they be calculated? And this is very, very intuitive. There's not a very scientific way of doing it. We do scenarios when we don't have much information, much data, and it's very approximate, very simple way of representing reality. Okay, so the best approach, the best scientific approach would be this, number 2. If we have good historical information, and if the model is correctly calibrated, and if we are aware of the model limitations. So if there are many ifs, and we solve these problems, then this could make sense. But this is what the problem is, that we are using science, and with science we are trying to solve a problem. So some problems can be solved, but again, models are simplifications of reality, and reality is incredibly complex to model. So we may be able to use the model, or maybe not. And this is an aspect that is called model governance that we are going to discuss later, right? So we were here, then here yesterday we introduced the value at risk, and this is the measure used in solvency, right? And here we have the sort of a mathematical definition where we say that L is a random variable, right? With distribution function f, big F, which is the cumulative distribution function, and an alpha is between 0 and 1. Most likely, alpha is 99 and a half, etc. And this concept was the investment bank J.P. Morgan, they say that they invented value at risk. Value at risk was not invented, right? It's a percentile measure, so it's a characteristic of a distribution. Basically, it's an upper percentile measure, and but they popularized the use of this measure to or the use of this metric to measure market risk, and banks measure market risk every day, right? It's not like insurance companies measuring market risk every year or every few months. Banks measure their market risk position every day, right? And because they have to do it, right? And they measure their risk, the portfolio risk over the next 10 days every day, and in 1994, the head of the CEO of J.P. Morgan, the investment bank, Mr. Weatherstone, popularized this the 415 report. And the 415 report is that he wanted at 4:15 p.m. one page with the summary of the market risk of the bank, right? Cannot be 2 pages, cannot be 10 pages. 1 page, right? And cannot be delivered later than 4:15 in the afternoon. So each afternoon at 4:15, he had to have the value at risk of the portfolio, and this was known as the 4:15 Weatherstone report. And then the industry, the banking industry, started to use the value at risk extensively. And also, JP Morgan even created this company called Risk Metrics, based on the methodology to calculate value at risk, which is, again, is a very simple thing to do, right? Now, some distributions have compact formulas, not all, but some distributions have compact formulas for the calculation of value at risk. And remember that yesterday we were dealing with a normal distribution, and then we say that the value at risk is basically the mean times the mean plus the standard deviation times the inverse of the cumulative distribution function at alpha. All right. So here in the table, in the first line, is a normal distribution, mu and sigma, and then this is the value at risk. Okay. So we have that already, and this this thing here is the basically this is the inverse of the normal, right, of the standard normal distribution. Then the T distribution, right? T distribution. T is another distribution very widely used, which has fatter tails than the normal distribution, and it's also symmetrical, and it has 3 parameters: the mu, sigma, and then the nu, and the nu are the degrees of freedom. Then exponential distribution, right? Exponential, another type of distribution that can be used with 1 parameter, has this type of value at risk compact formula. And then the Pareto, here I put Pareto type 2 because there are many Paretos, many definitions of the Pareto distribution, but here we have a compact formula as well. In most cases, we won't have a compact formula. Also, the log normal has a compact formula. But in most cases, we won't have a compact formula, so we have to do the calculation via Monte Carlo simulation. And what we do is that we generate a very large number of random deviates from a distribution. So we have an underlying distribution. We do this generation, and if you use software like R, it's very easy to do this. And simply we generate, say, for example, 1 million random deviates, and then we calculate where the 99 percentile is at. Or we can also calculate the tail value at risk, which is the next slide, and we are going to do the implementation later on. So here we have, again, an integral from alpha until 1, right, which is the upper limit, and L is again the loss random variable with a distribution big F, which is a cumulative distribution function. And here we have the only requisite here is that we have a finite expected value, right? So now some distributions do not even have expected value, right? Because they have very fat tails, and that doesn't exist, right? So T value at risk is the average value at risk for all alphas, and is the second most widely used metric in practice. And this is the most widely used in Switzerland. Okay, in Switzerland we use that all the time. And also here we have compact formulas. Look horrible here, but once you implement them in your system, you don't have to worry about that. So this is just algebra, and they are not so difficult to derive. Also for these same 4 distributions. Now the normal is not a distribution that can represent certain phenomenon, like severities of insurance policies. We use it for certain types of risks or certain types of situations. For example, yesterday we had a model what we 10,000 policyholders, and then we said that each one of them, or the loss of each one of them, represented a random variable, and then I used an approximation called the central limit theorem approximation, whereby a large number of the sum of a large number of random variables starts to behave like a normal distribution. That's why I was allowed to use it. Okay, so these two things are simply metrics, simply characteristics of the distribution. Okay, now there's a very, for those of you who are more mathematically oriented, there's a paper by 4 or 5 academics. The first one is Artsner and Delben, Artsner, and I can't remember the names of all 4, but they popularized in 1999 something called coherent risk measures, and it's a very, very fine paper. They talk about the characteristics of measures that have to be coherent and that they are very robust. And basically these desirable characteristics are defined in a so-called linear space of random variables M. And here we have this row represents the risk measure that takes me from M to the set of real numbers. Okay, and let L be a loss random variable. So the first one is called monotonicity. So if we have 2 risks, L1 and L2, right? In this set M, and L1 is less than or equal to L2, the risk measure of L1, if the risk measure of L1 is less than or equal to the risk measure of L2, then we comply with monotonicity, all right? So we want our risk measure to be monotone, okay? So that's one concept. So the larger risk, the larger the risk measure is, okay? Then the second one is called translation invariance, and here we say that if we take the risk measure of L, big L, which is a random variable, and we add small l, which is a constant, okay? So if we add L to a position, little l to a position with a loss big L, we alter the capital requirement accordingly, right? So if we take the risk measure of L plus L, this is equal to the risk measure of L plus L, right? Where L, big L is in the set of the possible outcomes, and little l is simply a constant. All right. So this is, if I'm measuring the risk, right, the risk of assets, and then I put an additional 10 million, then the risk is going to be the risk of these assets plus 10 million is going to be exactly the same as if I measure only the whatever is random, right? So this is called translation invariance. Then the third is called sub-additivity, and this is very important. If I measure 2 risks together, okay, L1 and L2, this has to be less than or equal to the risk measure of L1 and the risk measure of L2. And this is very easy to think of. For example, if you take the variance, okay, so the variance of x plus y, which is greater, this one or that one? Assuming that this is not stricken out. So if this is positive and the variance is always positive, and this is also positive, right? And then we say that this expression here could be less than, because we could have a minus here than the sum. All right. So this is a very important, the sub-additivity, And one thing that causes problems is that the value at risk measure sometimes is super additive, right? So if you consider the several random variables at a time, the risk measure should be less than or equal to if you consider the risk measures individually. Okay, so in some cases, value at risk is super additive. And these are the circumstances whenever the random variables are skewed or the random variables have a special dependence, for example, functional dependence. So functional dependence is when one random variable is a function of another random variable, right? So for example, if I have this type of thing, right, y equals x squared, where y is a random variable and x is another. Say that x is a random variable, normal 0, 1. Y will have a behavior that is linked to x by a functional dependence. But even though this is there's a functional dependence here, if you try to calculate a correlation coefficient, you will see a surprise, right? So you will think that if I have functional dependence, I have perfect correlation, and this is not the case, right? So many people are concerned about the use of the value at risk measure in certain circumstances won't work. Okay, and this is again. There were many criticisms in using the value at risk measure in Solvency II. At the end, they decided to leave it there. They said, well, in the majority of the cases, it's going to work. It's easier for companies to calculate it, which is not a very strong argument because nobody's going to calculate the measures. They are going to be calculated by a system, and it doesn't matter if the formula is very complex. It's already in the system. The idea is that it seems as though value at risk is an easier concept to understand than talking about an integral, right? So that bothered some practitioners, and then they decided to stick with the value at risk measure. Works okay, and the standard formula of Solvency II is less than perfect. It's not a perfect thing. So if you think that Solvency II can be adapted to other markets, well. You can take ideas from Solvency II, but adaptation is perhaps you cannot copy and paste, copy from what works in Europe and basically adopt it as is in Brazil. You have to do several adaptations, which is basically what the Brazilian solvency is doing, adapting, taking certain elements, but then having some modules or sub-modules that are adapted to the Brazilian business environment. Okay. Then the last one is called positive homogeneity, and this is basically that if I multiply L, right, by I multiply L here by lambda. Basically, this is equal to multiplying the risk measure of L times lambda. Okay. And this is a coherent risk measure. So here I have a summary of all the different circumstances, multiplication, linear combination, etc. So if this happens, right? This means that L1 and L2 are coherent. So a coherent risk measure is the L's are not coherent. What's coherent is the rho. So the rho is the function or the risk measure. So a coherent risk measure is a risk measure rho that satisfies monotonicity, translation invariance, self-additivity, and positive homogeneity. Okay. So if this happens, then you're on the safe side. And tail value at risk passes all these tests, so it's by far from the purely theoretical standpoint is the best measure. much better than value at risk. Not saying that value at risk is wrong, but under certain circumstances, it can produce results that may not make sense. All right, so just to keep that in mind. So this part is really, really theoretical, and then again, you can Google this name, Artsner, and you will find the paper, which is very good paper. If not, drop me a mail and I'll give it to you if you're interested, right? And this is if you like mathematics. If you don't like mathematics, then skip this part, right? And you won't miss anything. You won't miss anything. This doesn't add much. It's just that well, basically you have sometimes you want to know why value at risk is used, and what are the cons and pros, etc. So this is not exactly very useful. But anyway, here's the mathematics under the solvency capital requirement. Okay. So the solvency capital requirement, so this is the formal definition, is the amount of capital that enables the insurance company to meet its obligations over 1 year, and this is important. They said, why 1 year? And somebody else said, why not? Right? And it was decided that 1 year was the right horizon. But when Solvency II was being constructed, they thought, well, why not for the rest of for a longer horizon? Why not measure the solvency position in a longer horizon? And then they say, no, the only thing that is perhaps more reasonable is to make sure that you are going to be solvent the next year. That's it. Okay, so 1 year at a time. So in year 2019, you do your valuation 1st of January, like I said. That's a big difference with IFRS 17. For solvency, you do your valuation is beginning of year. For financial reporting, basically it's end of year, right? For practical purposes, you are going to be working every day, right? In producing numbers and adjusting models and calibrating and collecting information and cleaning data. But anyway, the calculation, the valuation of in year 2019, companies have already submitted the reports, okay, and so they have demonstrated to the supervisor, to the regulator, on January 1st. Of course, they do the calculation on January 1st, but usually in the Swiss case, for example, you have 4 months to deliver to file the results with the regulator. So it was until end of April this year that companies demonstrated that they are in a solvent position for 2019. Okay, so this delta t is equal to 1, probability alpha equal to 0.995. That is, I'm going to be solvent 199 times out of 200 times. Okay, and then maybe if somebody will ask, why not being solvent 200 times out of 200 times? Well, this would be perfect certainty that you're going to be always solvent. So you would have to charge a premium that is incredibly high in order to make sure that you're solvent all the time. So there's I guess the 199 times out of 200 is basically some form of a simplification. It's not that for practical purposes you say I'm solvent all the time, but it's really 199 times out of 200. And then again, if you wanted to mathematically, if you wanted to be solvent 200 times out of 200, you would need infinite amount of resources mathematically, right? So let V denote the capital, then the insurance company determines the minimum amount of extra capital called X0 to stay solvent at delta T. Delta T is equal to 1 year. with probability of at least alpha. So I'll let you read this. So this is just algebraic manipulation. So this is the definition, formal definition here, and from here, if you follow, everything is algebra. There's nothing very difficult about that. Okay. Conclusion: the solvency capital requirement is the sum of the capital available today and the capital required to stay solvent in delta t with a certain probability. If x0 is less than 0, that means that I'm already solvent right now. I'm already solvent at the beginning of year, so I don't need to do anything, right? So if I have lots and lots of capital, then I'm okay, right? And well, it happened that many companies are quite solvent, okay? And even when they were doing the quiz studies, the typical company was solvent, right? So it was not like many companies were in a difficult position. A few companies were in a dangerous area, okay? But the majority of the companies were solvent. Now, what's the typical solvency ratio in Europe these days? About 160, 180, more or less. So that means 180% of the solvency requirement. So that's the capital that they have, right? And this goes up and down. IOPA publishes statistics about solvency results, but the typical companies at 160%, 180% of solvency requirements. And the typical reinsurer is even more solvent. So reinsurers tend to have more available capital for solvency. So I know that Swiss Re ended the year with 225% or something like that. I need to double check that number. But about that, so they have more than twice the solvency capital requirement. So, yeah. So here's the mathematics behind the solvency capital requirement. Now, what's the complexity here? Well, now the complexity is that we need to translate this last equation, okay? We need to implement this last equation, right? And that's the complexity. That's the whole exercise. Now, our good friends from IT were trying to connect the projector and everything because, yeah, I need to show you some numbers that are here in this one computer. So we will presumably we'll be able to achieve that after lunch and go through the illustrations. But anyway, some of these illustrations are here in the slides, but it's better to look at the whole process to understand. Okay. So any concern about, any question about this slide? Yeah, this is another one that you can print out and put in your living room, if you want. Now, better not, because you're going to scare your guests. You know, they come and they see this type of things, they're going to run out. But you can put it in your office, right? And then if your boss comes, he's going to be impressed by what you're doing, right? Okay. Now let's look at some examples. First of all, let's start with a market risk example, right? And here we use this this is our standard in Switzerland. We use it all the time, and this is what the regulate. This is a method that the regulator basically makes available, right? Proposes this method as simplification, and it's a very, very beautiful simplification of the market risk. And here's the story. The thing is that we have to calculate the solvency capital requirement for market risk. Okay, so so we have this variable solvency capital requirement for M market. be the capital requirement for the market risk. Now, this is a variable, and then we say we are going to approximate the value of that function with and the value of this function depends on a collection of risk factors. Okay, so what we want is that there's a way to approximate functions. All right, so we learned in calculus that that we can approximate functions using a Taylor series expansion. You remember that? So, and what is that? Well, a Taylor series is a polynomial. So, with a polynomial, we can approximate the value of a function, right? Taking the first the function, then the first derivative of a function, second derivative, etc. Whatever number of derivatives we want, and then there's an error term. So this is very useful thing in calculus, and Taylor was a great British mathematician. He's not as famous as Newton. Newton is considered one of the fathers of calculus. Because they live at about the same time, and Newton also had these laws of physics and the description of the orbits of the planets and so on and so forth. So Newton was at the end was very famous, and Taylor was not so famous. But anyway, when we learn calculus, we have this Taylor series formula, Taylor series expansion, and the idea is beautiful. It's a beautiful idea. We can approximate the value of a function with a polynomial. What's a polynomial? Polynomial is a sum of many terms, right? So what's the mathematics? Here we have that the solvency capital requirement for market is a function of certain risks, random risk factors, which we put in this vector, right? At time 1, what is time 1? Time 1 is the end of the year. We are now in time 0, okay? So this is basically a function of t and set t, right? Where t is going to be equal to 1. So this is we have the factors, all right? And we are going to evaluate everything at t. So, and this is the vector, all right? So using the first two terms of the Taylor series expansion, we are going to evaluate the solvency capital requirement of the market risk considering the random risk factors at time 1, end of year. And this is going to be approximately equal to what? To the solvency capital requirement of the risk factors at time 0 plus the first derivative, right? Also at time 0 with respect to each of the factors. So this I goes from 1 until D, plus the second derivative, and then we have, if you're interested in the Taylor formula, go to Wikipedia and then you find the explanation, right? But for, basically the Taylor series expansion tells me that here I need 1/2, and then I take the second derivative, right? And so on. So basically I take this delta solvency capital requirement of market risk at time 1. So the delta is basically this first term. I put it in the other side of the equation, and then this is here. So this minus that is called delta solvency capital requirement. So here are the terms, and then I put the also at the end the matrix notation. So I use matrix notation as a thing that I need to estimate. Okay, and of course, all this thing, this plus that, is itself a random variable because I have random factors. Okay, so now my task is to calculate this expression here. Okay, and this is the underlying theory. All right. Are you good here? Okay, and just one last comment that this is Later we explain why, but this is a suitable approximation of the required capital for certain market risks and also for mortality risks, okay? Later we'll tell you why. Now, here's graphically what we are doing. Let's say that the function that we are trying to estimate is this orange line, right? So it's this orange line here, this function we're trying to estimate. Now, if I take the first term or the first derivative of the Taylor series expansion, I will have this red line. Remember the concept of derivative, right? So the derivative is a line that is tangent to a function. That's a concept of derivative. Okay. So the red line would be taking the first derivative. Now the second line is basically called the delta gamma approximation, right? So practitioners call it delta gamma. The first one is called delta normal approximation. The second one is called delta gamma approximation. Okay, so that's the graphic explanation. And then if we look at the axis, y-axis is the solvency capital requirement at time for market risk at time 1. And then if we look at the x-axis, this is basically the characteristics of the function. Of the collection of risk factors. Okay. Now, this random variable, I put it on top. The random variable, this is delta transpose times x, but x, right? X is in bold, so x is a matrix, plus 1/2 of the transpose x matrix times gamma, right? So this is uppercase gamma times x. Okay, so this is a matrix notation, and matrices are very powerful, particularly for software implementation. They are very easy to work with. So through the delta gamma, we obtain a RV, random variable that models the underlying risk. What's the underlying risk? The market risk. Okay, and what is market risk? Well, this is the risk that my solvency position or my capital is going to change because there are certain factors like changes in interest rates and so on and so forth. So I have this, again, this delta solvency capital requirement at time 1, then x, which is x at time 1, is a collection of small x's, right? Where each one responds to the changes in risk factors. Then I have delta, which are the sensitivities, right? And what are the sensitivities? Well, I go back. Sensitivities are the derivatives. I see how sensitive is a function to the change in the underlying variable. That's a sensitivity. Okay? So I have a delta sub I, right, which is here the derivative with respect to the set factor, and then I have a gamma I sub ik. Now the gamma is has two indices, I and j, right? Why? Because I go back. I don't need to go back. Here I have it's a second derivative, so I derive this twice with respect of two variables. It is assumed that the risk factors follow a normal distribution, and therefore x is normal. And we obtain random vectors that follow a multivariate normal distribution, right? Which is quite easy to implement. Okay. Now, I have the sensitivities here. Now, how can I tell the computer to compute a derivative, right? A derivative the derivative is a concept that is sometimes is a bit tricky because a derivative is about the instantaneous rate of change. So that's the definition. But change happens between one point and another point. So can a change be, can we have an instantaneous rate of change? Can we? Well, no, we can't, because whenever we cannot have instantaneous change. Change needs to happen between 2 points in time, right? So there's a gap, right, to have change. But anyway, in mathematics, we say that the derivative is nevertheless the instantaneous rate of change. Okay, so we say that, and we are basically calculating the tangent line to a curve. So, but I need to tell this to my computer, right? My computer can't deal with derivatives. Well, maybe they can, because I take that away. There's under normal circumstances, the computer cannot deal with derivatives. I have to do the implementation. And what's implementation? Well, very simple. And this is if you remember the definition of derivative, you know, the limits and all the rest, you see that implementation here involves adding a small increment, which is here we call h, and subtracting that small increment. So hi is the same thing, dividing but by 2 times the increment. So that's implementation. That's the estimation of the first derivative, which are the elements delta sub I of this vector. Okay. Now, in the case of gamma, right? Gamma is not a vector. Gamma is a matrix. So I will have certain elements that are in the diagonal and many elements that are not in the diagonal. So if you are in the diagonal, what I do is that I take set plus h, set minus h, set, and then I divide. Well, I could have put this in the same denominator, in the same fraction. I did 2 fractions for the sake of clarity. This is if I am in the diagonal. If I am not, so here if I is different than k, then I have a set I plus h, I, set k plus h, k. So I have plus plus, plus minus, minus minus, minus plus, which are all the different combinations. And here the denominator becomes, whereas here we have hi squared, here we have 4h I hk, right? So this is the implementation. Now, sensitivity not implementable in the computer. Estimation very easy to implement in the computer, right? Okay, so what I do now is this is the example. This is so we have seen the theory, then we have seen basically the implementation procedure, okay? And now let's apply it to something. It's a real life problem, okay? So this real life problem, not so real, but anyway, let's consider an endowment policy. Do you know what is endowment policy? All right. So sum insured is $1 million per person, okay? Term is 10 years, okay? The portfolio consists of 100 policies. Everybody's exactly same age 40, and everybody has the same sum assured. Now we see already that this is a kind of a simplified problem. So we start with some theory, some general theory, and then we do the implementation in a very simple problem, which is this. Okay. Now, deterministic mortality, and when I say deterministic, I mean we use the mortality table and we use always the same values. Mortality is not going to be subject to a random process. So we use the mortality table as is, and we are going to shock the mortality table. Okay. We have spot rates, which are the risk-free yield curve denominated in US dollars. Remember that this is a product, the sum assured is in dollars, and then to avoid currency exchange risk. I have my assets in dollars, my liabilities in dollars, everything is in dollars here. So I don't have currency exchange risk in this particular example. And then I'm going to invest the assets in US dollars, like I said, and I have a market value of these assets of $105 million. So I have assets in the amount of $105 million, okay? And I invest these assets in a basket of stocks and also in zero coupon bonds in terms of 1, 2, 3, 4, until 10 years. So I have bonds of different durations or different terms, okay? And then I also have a basket of stocks, and then the sum of all these pool of assets equals $105 million, okay? Now, question, management question. So with all these formulas, the confusing formulas that you showed, so what do I have to do now? What do I have to do? Well, I have to calculate how much solvency capital I need to set aside to support this business. That's the task, okay? That's the task. So now that you're armed with this theory, okay, what's the next step? Any clues? What would be next? What would be next? Hmm?
Other assumptions like churn, like return of assets.
Yes. We need the very good. We need the asset returns. Very good. Yes. Very good. What else? Well, we need to identify what are the risk factors, right? What are the risk factors? Because the risk factors are going to drive my solvency capital requirement, right? So I need to know the risk factors, but also I need to know what are the interest rates, right? So I have this pool of assets, and then I have certain expected returns. I need that, and then risk is going to be defined by pretty much by changes in the risk factors, right? But see, one of the problems here is that I need to find a practical way of calculating this function, right? And I have many things happening here, which may affect my solvency capital requirement function. So yeah, so for the implementation, I'm going to define 12 risk factors as follows. I have 10 spot rates, so I have interest rate for 1 year term instruments. I have another spot rate for 2 year term instruments, etc. Right? And these terms have to be these rates have to be denominated in dollars. Then I have a stock index factor because I am also investing in a basket of stocks, and then the value of this basket of stocks can change. I don't know how much, but I need some risk measure to try to forecast that. And then I have so I have 12 factors. So 10 different interest rates. One is the change in the stock market or the stock index factor, and then I have one other risk that is called mortality, right? Mortality, because I don't know how many people are going to die, etc. Right? Then I will have H. H is the vector of changes in risk factors, and this is I have 10 times 0.01. The 11th element of this vector is 0.1, and the 12th element is also 0.1. So it's 10 times 0.01, then 0.1, 0.1, okay? So these are going to be the shocks. I'm going to shock my factors. And a shock can be additive or can be multiplicative, right? So let's use additive factors for the changes in spot rates, and let's use multiplicative factors for the change of stock prices and mortality rates. And this is an arbitrary assumption, okay? So what do I mean by that? Something can change by 1%, but what's the meaning of that? I add 1% or I multiply what by 1.01%? What is exactly what goes on? So that's the difference between one and the other. But then in the implementation, we will see. Okay. All right. So we cannot do the implementation because of the technical difficulties. But after lunch, we continue with that problem. But you understand what the problem is, right? So I have to estimate the solvency capital requirement for market risk function. And I'm going to approximate that with an algorithm that I described, and then I need to recognize the factors. I know that I have in my balance sheet, I have $105 million. I also need to calculate the liabilities, right? I need to calculate the liabilities because I'm taking premium. How much premium am I taking? I don't know. In this problem, they don't tell me, but basically. I have risk factors, and also, what is the business I'm in? Well, I am selling 100 policies, and then I need to basically estimate the cash flows, right? Which we will do. So we will have a full explanation about this, how we implement this model. When we have when I can show you. The mechanics. So that was first problem. Second problem is a different. Now, everything that I spoke about, put it aside. Now we are going to talk about the Solvency II approach, right? So what I said before is not the Solvency II standard approach, but it's an approach that is used by the Swiss solvency test. So by that, I am exposing you to different ways of calculating market risk. Okay. Now, this is how Solvency II does it, right? So remember that we have in this standard formula, we have many boxes. Well, one of these boxes is called market risk, and then market risk has many soft modules. It has, for example, the interest rate submodule. Okay, so this is the risk that interest rates change, and if they change, my asset position is going to change. Also, I have equity risk. Also, I have property risk. So this is the risk that real estate prices change. Spread, right? Spread basically is spread above the risk-free rate. Currency risk. Many companies have assets and or liabilities denominated in different currencies. So if there's movement in currencies, I have risk, right? Then I have something called concentration risk, right? And concentration is very easy to understand. Everybody, actuaries and non-actuaries, understand that if I put all eggs in the same basket, I have more risk. That's a concentration. And then I have another one which is called illiquidity risk. So illiquidity risk is the risk that I have to pay expenses or pay claims, and I don't have money. When that happens, I have to either sell an asset in a hurry, and then probably I will not get a good price because it was something that I had to do very fast, right? Or maybe I have to go to the bank and ask for an emergency line of credit. So that's illiquidity risk, and that's basically the risk that was very, very prevalent in 2007. The housing risk in the United States that had consequences everywhere in the world, and then with a major impact also in Europe. And Europe had after the liquidity risk in 2007, had another risk called the euro crisis, right? So where central banks and then the European Central Bank were making all efforts to save the euro, the currency. And then many countries, for example, Spain or Greece or Ireland, Italy, started to have severe economic problems. The problems are more or less solved. Not everything is solved. European economy hasn't really recovered. U.S. economy has recovered. U.S. economy seems to be very strong, right? After a few years after the crisis. Europe has not entirely recovered. It's in a better shape now. Now there's a different type of crisis, which is the political crisis now. And there were elections for the EU Parliament in Europe. And just this morning, I heard of the new president of the European Commission, lady Ursula von der Leyen, who used to be defense minister of Germany. So we are entering a new phase in a European politics, and let's see what happens. There's a lot of problems going on in Europe and integration, and we also have the Brexit, which is imminent, and this is going to have impact in a society, but also economic impact everywhere, etc. Right? So all this to say that all these things that happen can be translated into risks that are in this particular instance captured by market risk. Okay, everything that goes that impacts macroeconomic variables that has a direct impact in my balance sheet. Okay, now definition, and these are the Solvency II words. Risks that arise from adverse changes to a company's financial position due to changes of market prices of financial instruments. I said the Solvency II words, but a little bit streamlined because they the law is Solvency II is a law, so they have more words. But I have taken away some words that are not indispensable, and I have focused on this short definition. Risks that arise from adverse changes to a company's financial position. Financial position, where is financial position? My balance sheet. Due to changes of market prices of financial instruments. Methodology. Here we follow a so-called modular approach, and we use linear correlations used for the aggregation of individual components. So I have these 6 components, right? Or 5 components in the matrix. We have 6 illiquidities treated separately. But we have here a correlation matrix also provided by the regulator, right? And be careful when reading this matrix, because we have some strange notation here. For example, correlation between equity and interest rate, can be either 0 or minus 0.5, right? Now, the idea here is that you use whichever factor produces the highest solvency capital requirement, okay? Because remember that these risks affect not only your assets, but it may also affect your liabilities. So if there are movements in interest rates, what happens? Well, if I have only assets invested in bonds, for example, I know that if interest rates increase, then the market value of the bond decreases, right? But here, if what happens if I change an interest rate? What happens to a life reserve, for example? How does a life reserve behaves? So you may find some complications. So what you have to do is to test both correlation factors, where there's 2, and then use the factor that produces the highest risk. Okay. So and here again we find our good friend, the standard deviation type formula, right? we have the entries of the correlation matrix, and then we have to take all possible combinations, okay, of all these risks. Now, if I don't have, say, all my assets and liabilities are denominated in the same currency, in reais, for example, I don't have currency risk, so I can ignore that. That's clear, right? The same, if I don't have equity investments, I simply ignore that. Now, interest rates of modules. So we are, I go back, okay? So here we are at the market risk level, but we need to calculate each one of these boxes. So I'm in the second box here, sorry. I'm in the second box, and this is the interest rate risk. Now, what they do is that, first they define it. These are the risks that arise from adverse changes to a company's financial position, balance sheet, due to changes in interest rate curves. Methodology. Well, there are prescribed instantaneous shock factors to interest rates. And here we introduce a concept called NAV, which is net asset value. Net asset value is another word for assets minus liabilities, right? So the risk is measured as impact on net value of assets, NAV, when rates go up or down, including adjustments for future discretionary bonuses, FDB, future discretionary bonuses. What are those FDBs? FDBs. These are bonuses that are paid to policyholders, right? That are discretionally paid, right? So it's like I pay you if the results are good. If the results are not good, I won't pay you. So that's a discretionary bonus, and if I have that, then I can argue that I need to do an adjustment. So my solvency capital requirement is basically for here I'm talking solvency capital requirement for interest rate risk is the basic solvency capital requirement for interest rate risk plus adjustment, and the adjustment is defined as this thing here minus the minimum of these two things, right? Where I have a superscript A, which A means adjusted, right? And also I have this is how they present the formula, right? Which is I don't know why they do it so difficult, but basically this is a straightforward formula. There's simple arithmetic to do that. Now, the shocks are given here in this slide on the right-hand side. So here, basically, they say for interest rate, for the interest rate for a 1-year term instruments or the 1-year spot rate, shock it, increase it by 70%, right? Or decrease it by 75%. So you do these shocks, and then you see what happens, right? For the 5th year, for example, increase it by 55% or decrease it by 46%, right? Now, these factors, where these factors came from, well, I don't know. I think they were I don't know, they were the result of quiz studies, calibrations, whatever, and then the regulator decided that these were the right shocks, okay? And that's it. So that's the what we have to implement now, right? So, which is easier? The model that and it's a bit unfair that I ask you this question at this time because we haven't seen the implementation of the first model. But so we have only seen the mathematics, the formulas, but I would anyway ask you which one you think is easier, the first one or this one? Implementation of this one is, in Excel, I do it in 1 minute. Well, the answer is that this is much easier, right? The other one is not difficult. It's not difficult, but it's more, how do you say, you have to do a little bit more programming. The other one requires programming. This one requires Excel. Or you can do it with pencil and paper. There's nothing wrong about it. Now, the purpose of me presenting you two different models is to tell you a standard formula solution of Solvency II in Europe, or tell you also sort of a regulatory model in Switzerland. Okay, so the two are relatively, they are very common, very, very common. Okay. So the first one has basically is an approximation, and has has certain underlying assumptions. For example, a normal distribution. Here, I don't see any probability distribution. I don't see anything like that. Still, I have the concept of shocks, right? So the concept of shocks basically makes me think of the third approach I was referring to earlier, right? So it's like a sort of a stress test approach. So I shock the rate. I say, well, what if rates increase by 70%, or what if rates decrease by 75? They increase by 70, they decrease by 75. What happens to my balance sheet? That's what I do. So I'm shocking the balance sheet, or I'm stressing the balance sheet, and see what's my net asset value. And then basically forget the adjustment for now, which is basically difficult to look at. But here we take whatever is greater between the increase in net asset value, if the rates go up, or the increase in net asset value if the rates go down. What is, again, net asset value? Assets minus liabilities. Now, not that fast. Assets, there's a full definition of what are assets, what kind of assets can be admitted, right? And liabilities, liabilities are basically the technical provisions. So there's another set of rules for that as well. So it's here I'm showing you arithmetic formulas that you implement in 1 second, but then there's a lot of work behind it, right? It's not that straightforward. Okay, so we still have a few minutes, so we can do another example of the Solvency II, and here I will show you also the Excel implementation. So let's say that for this second case, a company issues an investment contract with an annual discretionary bonus. Okay, there's no mortality risk, so this is like an investment. No mortality risk. Assets are invested at the risk-free rate, and liabilities are replicated using risk-free bonds. And the cash flow estimates are like this, all right? So I have you would say, and where's insurance risk here? Well, there's no insurance risk. But the only reason that I'm doing this is that I'm calculating a standalone market risk. If I put mortality, then I have to do other things, right? So I'm like separating the market. I'm basically presenting a product that has only market risk. Okay, so I have the cash flow estimates as follows. First of all, I have the rates here. Yeah, well, here this is the expected risk-free rate. So these are the risk-free rates that are observable, right? Denominated in US dollars for different terms. Okay, ignore now the shock rate because now there's no shock here. Then this is a guaranteed rate. So I'm going to pay to my investors or my policyholders, I'm going to pay 0.5% I need to look at the spreadsheet. I need to pay a bonus but this bonus is discretionary. I'm going to pay it only when certain conditions are met. So it's a discretionary bonus. More on that later on. Then I have these amounts in zero bonds. Okay, these are dollar amounts. Then this is the present value of assets, and basically I do a backward calculation. So these 50 in 8 years. If I take the present value of that is 45, so I must be dividing this by 1.2%, 1.02% or something like that. So I take the cumulative amount, and then I reach 4,068. That's why I want to see the spreadsheet to know exactly what am I doing here, right? Then I have some replicating cash flows, right? I have a statutory reserve. So I need to explain how we calculate these numbers. And then here's the rule for the bonus. The bonus is a function of the reserve, and I'm giving this 0.5% of certain function of the reserve. I think it's 90% if I remember correctly, but I need to look at it. Then I have the cash flow of the benefits, right? Which is nothing but this column plus the bonus. And then I have the present value of the liability. So I see that the present value of the liability today is smaller than the present value of the assets. So we are dealing here with a cash flow exercise. And here there's no mitigating effect, right? So the mitigating effect is that if I have some money set aside, this money counts as capital in case of an emergency, right? So that's a mitigating effect. I illustrated that with the session before lunch. I said that deferred taxes have a mitigating effect. What's the meaning of that? Deferred taxes are taxes that I set aside some money to pay taxes in the future. So this is the concept of deferred taxes. But according to the solvency rules, if there's an emergency, I can take this money to pay to stay solvent. That's a mitigating effect. So I may have a pool of assets to pay bonuses, but I can use this money to stay solvent. So that's a mitigating effect. But then I have in my spreadsheet, and this is a spreadsheet, a very easy spreadsheet. I have a mitigating effect. So my net asset value is what? 129, right? And then here, let's see. No, I don't have here. I don't have the whole story. No, I think it's best that we stop at this time because I really want to show you the spreadsheets behind this, and also I'm going to contrast this with the first model, and let's see what what conclusions we can take from these two different market risk models. Okay, so there's we are about 5 minutes earlier, but I think makes sense to stop at this time and continue at 1:30. Okay, so enjoy the lunch. See you later.